So, uh, in this video, we'll be talking about positive feedback uh, and and uh, and how this positive feedback leads to BARKHUESEN criteria. And certainly, if we go back to the concept of transistor, we better understand that a transistor can be used as an oscillator. So, uh, so when it comes to oscillation, I mean, if we take a simple concept of a spring and we let it oscillate and leave it for oscillations, it's going to oscillate for some time, and slowly the amplitude of its oscillations will go on decreasing. So we call such oscillations as damped oscillations. And in order to sustain the oscillations with constant amplitude, we have to apply the external energy for the system, so that the system retains the constant amplitude. Now here, we would understand how positive feedback maintains the the amplitude of the oscillations, and how it leads to Barkhusen criteria. Now, to start with, if I go back to the concept here, we have we have we have an amplifier, and then let us assume that the gain of this amplifier is A. Then we have a feedback circuit, and let us assume that beta is the feedback ratio. And then we will have the input, and we will have the output, and a part of this output is subjected back to the feedback circuit. Now, we have a better understanding of positive feedback once the signal passes through this feedback circuit. This is our feedback circuit. Once it passes through it, we should be in a position to uh, uh, the signal with same phase with respect to the input signal. So we have a signal, right? And then this signal is amplified, and this signal is subjected to the feedback circuit, and we obtain a signal out here. And we can see here that there is either no phase shift between the input and the feedback signal that we have obtained through the feedback circuit. Or at the most, we can have a phase shift of 360-degree. So the things are quite clear here. I mean, we can use common base configuration here. We can also use common emitter configuration. If we use common emitter configuration here, then here I will get something out of phase with respect to the input signal. But then the job of the feedback is that it has to again change the phase of the signal that will be coming from this V out to the feedback circuit, so that the signal that we have subjected to common emitter will come in same phase once we obtain this at the at the feedback circuit. So here we have output, here we have say input, and then here we'll have something like VF, what we call as VF voltage, the feedback voltage that will be obtaining here. Now the point is that if I start my loop starting from here, so this is my input voltage VI, and here I'll get output voltage. This output voltage will be VI times A. This is clear because the voltage gain is given by V out by VI, and then proceeding in the same fashion. So this V output will be it will be the input for the feedback circuit, and VF I'll obtain here. This VF will be beta times V out. But from this equation, it's clear that V out is VI times A, then VF will be A beta VI. So here we are analytically trying to attain a relation between the feedback voltage that we obtain with respect to the initial voltage that we have given to the amplifier. So now let us proceed from here in a way that that suppose I take a case here. I take a case here as case one. I design the circuit in a feedback circuit and the gain of the amplifier in such a way that A beta this A beta is less than 1. Now, if this A beta is less than 1, what is going to happen with VF? VF will be less than VI. I think it's clear up to here. Now, if we move on, in this case with some example. Now let us suppose that my VI, suppose my VI is 2 volts, and A beta is 0.6. Okay, if this is the case, what will be VF in this case? VF will be it will be 0.6 into 2. So this will be 2.7. Sorry. This is 1.2 volts. So what do we see here? We see that the feedback voltage that we have obtained, it is 1.2 volts, right? Now, if we proceed with another number with same initial voltage as 2V, and fix this A beta as, say, for example, 0.5. Okay, so in that case, what will be VF? That will be 0.5 times 2, so that will be 1 volt. Now this is a way to understand the situation here in terms of simple numbers. So what's going on in this case is that that if I have high initial voltage, this voltage is gonna decrease in its amplitude. So if I call it VO with respect to time, I'm going to obtain damped oscillations, right? So with the condition, if we assume that this A beta is less than 1, Now let us proceed for another case where we assume that this A beta, where we take this now we take the case 2, where we assume that this A beta is greater than 1. If that's the case, what will be VF? Because VF is basically, it is A beta VI, right? So in this case, we have VF greater than VI. And we can understand it with simple numbers. If we take the same example where we choose VI equals 2 volts, and here I'm taking A beta greater than 1. So let us assume that this A beta is nearly say 1.5. Okay, so in that case, what will be VF? VF will be 2 times 1.5, and that will be 3 volts, right? So we can repeat it for another term. VI is 2 volts, and A beta is, say, for example, 2 volts. Let us take it 2 volts. So what will be VF in that case? It will be 4 volts. So in this case, what's going on is that the effective voltage, the feedback voltage that we are obtaining back to the amplifier, its amplitude is increasing. So if I have to think it in terms of a graph, so if I have a signal like this, its magnitude is gonna increase. So this will be my output voltage, and this will be time. And then let's go back to the last case. The last case we can take on is assuming that let's have a case 3. In this case, we set A beta in such a way it is equal to 1. Now, if this is the case, what will happen to the VF, which is A beta VI? We will get VF equal to VI. So that means there is sustained amplitude. The constant sustained amplitude of voltage will be retained in the amplifier by virtue of positive feedback that we have subjected to the given problem. Now, if we go back to the gain equation, what is gain? What is voltage gain? Say voltage gain in presence of positive feedback. And voltage gain in presence of positive feedback. What's that? That's A dash equals A divided by 1 minus A beta. Right? So this is the equation that we have already achieved in our past videos. Now we can see here that the condition third that I was talking about, if I take A beta equal to 1, in that case A dash, now this A dash will be A upon 1 minus 1, that is A by 0. That implies infinite. Now this condition that we have achieved here, this condition, you have the gain in the amplifier, even if you don't have the input voltage. So this criteria that we have here in terms of positive gain for an amplifier, where we want a sustained oscillation, that means the oscillation will certainly have a constant amplitude. If we set beta in such a way that its value is nearly equal to 1. So if I assume this is V out and this is T, so here we have undamped oscillations. I should call it undamped oscillations. And uh, and this criteria that we have talked about here, this criteria is called as Barkhuesen criteria. So Barkhuesen criteria, it is an analytical identity that sufficed to a system where we have a positive feedback, and that positive feedback leads to undamped oscillations. That means the amplitude of the oscillations does not decrease with time. And we have a stabilized oscillation in our system.